Hello, everyone, and thank you for joining us today. Welcome to Megger's Testing Tactics webinar series. Today's topic is fundamentals of transformer commissioning and maintenance testing. My name is Michael Fleischer, and I'm the digital marketing specialist for Megger. I'll be acting as the moderator for today's presentation and supporting you on any technical issues or questions for our presenter. On the right side of your screen, you will see a control panel that looks similar to this one. You can submit questions at any time during the presentation by typing in the box highlighted in red, and I will read the questions out during the Q&A segment at the end of the webinar. Additionally, a certificate of attendance, copy of the presentation, and link to the recording of this webinar will be sent to all attendees in 2 business days. Our presenter today is Sanket Bolar, Applications Engineer. Also, to assist with the question and answer session, we will have joining us Daniel Carreño, Applications Engineer, and Charles Nybeck, Applications Engineer. All right, let's go ahead and get started. Thank you for joining us today, Sanket.
Thanks, Mike. All right, so let's get started with today's presentation. Before we head, I'd like to say what we are going to be doing in this presentation. We are going to be talking about transformers. We have done several presentations in the past where we have talked about individual tests and we have talked about those in detail. But in this presentation is going to be a little different. Here we are going to focus on the transformer itself. When you step out in the field to do testing on transformers, it's important for you to have a good understanding of the asset that you're testing on, right? To have a good understanding of the transformer itself so that you know exactly what's going on when you're performing those tests. So instead of delving on individual tests, and we are going to talk about transformers, and then we are going to talk briefly about the tests that are done as part of commissioning and field testing. Okay, so let's get into the agenda. These are the sections that we are going to cover. We are going to start off by talking about transformer theory. So we're going to start off from the very basics and see the physics behind how a transformer operates. Then we are going to talk about the components that are present inside a transformer. We are going to cover the critical ones. There are several components inside a transformer. We cannot cover all of those, but we're going to talk about the ones that are very important. Then we are going to talk about the nameplate data. When you step out in the field, the information that you go off of is the nameplate data, and the nameplate on the transformer. So it's important for you to understand the information that's provided on the nameplate. And there's a lot of information that's provided on the nameplate, and that's quite helpful. We are going to talk about how to interpret the data that you see on the transformer nameplate. And then the last section, we are going to cover all the tests that are done on transformers, typically as part of commissioning, as well as field testing. Okay, let's start off with the very basics, transformer theory. So what's the difference between alternating current and direct current? When we draw an AC waveform, we draw a sine wave. What does that sine wave mean? It means that the current direction basically changes every half cycle. So every half cycle for a 60 Hertz system is 8.33 milliseconds. So every 8.33 milliseconds, the direction of the current is going to effectively reverse. So that's why it's called alternating current, whereas for a DC, it's a straight line, which means that the current flows in just one direction, right? Current, when it flows through a conductor, it creates a magnetic field around it, and the direction of the magnetic field can be represented by this right-hand rule, where if you make your right hand into a thumbs up sign, then if the direction of the thumb represents the direction of the current, then the direction of the fingers represent the direction of the magnetic field lines that are created around the conductor. Now, if the current that flows through the conductor is alternating, that means that the direction of the current is going to be reversing every half cycle, which means that the magnetic field also reverses every half cycle. So the direction changes from clockwise to counterclockwise every half cycle. So what you get is an alternating magnetic field for an alternating current. There is a law called Faraday's law, which states that when a conductor is exposed to an alternating magnetic field, then a voltage is induced in the conductor which is proportional to and opposes the rate of change of flux. Flux is basically the lines of field that's created around the conductor, right? An alternating field is present here. So let's say I bring another conductor in the vicinity of this field, then a small amount of voltage will be induced in that conductor. Now, these two concepts are the basic concepts behind the operation of a transformer. So in a transformer, what do you have? What you have is a couple of winding coils, let's say, on a magnetic circuit. So the magnetic circuit is a core. Typically in a transformer, it's a certain grade of steel is used as the core, and then you have winding coils on that core. Now, what exactly happens inside a transformer? Let's say we have a transformer which is on no load, which means that the secondary winding does not have any load connected on it, right? So we have two windings here with different number of turns. One's N1 and the other one is N2. If a voltage is applied on the winding with N1 turns, let's say I apply a voltage of V1, it's going to draw a current called the exciting current or excitation current. Now that current, going by what we discussed in the earlier slide, it's going to create an alternating magnetic field. That field is going to set up in the core. So the core serves to channelize that flux. It's like you pouring water on the floor as opposed to pouring water on a conduit. Right? The conduit channels the water in a certain direction instead of the floor where it just spills all over. So that's the function, that's a basic function that it performs. It channels it so that it links with the secondary winding. The operation of the transformer, as you all might know, is to change the voltage level from one voltage to another. Right? How do we achieve that? What's happening is the field is being created in the core, and that field is linking with the secondary winding, and that's creating another voltage, that's inducing a voltage on the secondary winding based on Faraday's law. Now, the relationship between the two voltages is the same as the relationship between the turns on the winding coils. So basically, the volt per turns on either winding is the same, which means that the ratio of the voltage to the number of turns is the same, which means V1 by N1 or V1 over N1 is equal to V2 over N2, which translates to the voltage ratio is the same as the turns ratio, which is the reason why we perform a turns ratio test. So up until this point, we were assuming that there is no load connected on the secondary side. Now let's say we connect a load here. Now we have a voltage present on the secondary side. We have connected a load, which means that the load is going to draw a current. And when it draws a current, the current that is drawn creates another field or results in another what's called an MMF, which is basically a magnetizing force, which sets up a field which opposes the original flux that was present in the core. Now let's call this the secondary MMF or magnetomotive force. Now this MMF opposes the existing flux. So that's going to result in a reduction in voltage on both coils, and that reduction in voltage results in more in a proportional primary current being drawn on the primary side. So an additional current of IP is drawn in the enters the primary winding, and that results in the creation of a primary MMF, which basically cancels out the secondary MMF. So the blue flux and the red flux basically cancel each other out to restore the original balance that was present, which is which is called the magnetizing MMF. So what we have is basically an ampere turns balance being restored, which means that the primary current IP times N1 ampere turns on one side is equal to the ampere turns on the other side, which is the secondary current times N2. So taking both of these relationships into consideration, we arrive at this equation which states that the turns ratio is the same as the voltage ratio, and it is inversely proportional to the current ratio. So voltage, let's say, we can also say this. We can also say it this way, that the product of voltage and current on either side is the same, which is what's happening, right? The product of voltage and current is power. Power is coming in from one side. It's of course it's electrical power, and that electrical energy is getting converted into magnetic energy. That's getting converted back into electrical energy. What's changing is the voltage levels and the current levels. If the voltage steps down by a certain amount, then the current steps up by the same amount. Okay, so That's how a transformer operates. That's the physics behind how a transformer operates. Now, let's talk about a primary equation which is used as part of transformer designing. This is the basic equation, and it is derived from Faraday's law, which we mentioned earlier, right, where we said that the EMF induced is equal to and is opposes and is equal to the rate of change of flux. Now, based on that law, this is the equation that you derive from it, which gives you the relationship between all the basic parameters that go into designing a transformer. V could be the voltage on the primary side or the secondary side, doesn't matter. But whatever coil it corresponds to, it's equal to 4.44 times the number of turns of that coil. A is the cross-sectional area for the core, the magnetic circuit. Bm is the maximum flux density. So when you have a core in the transformer, you want to operate the transformer at its maximum efficiency, right? You want to reduce losses, or you do not want to use extra material. So when the transformer is operated, it's operated at its maximum. The same goes for the core. The core is operated at its maximum flux density. It's like you have a glass of water, you do not want it half full, you want to fill it up to the brim. And that's exactly how the core is operated. So the maximum flux density typically for power transformers is 1.7 Tesla. So that's the value of Bm is going to be close to 1.7 Tesla. F is the system frequency with 60 Hertz here. So this is the basic equation which a transformer designer has to pay attention to while designing the transformer. So based on this equation, he'll figure out what the number of turns on the coil should be, what the thickness of the what the cross-sectional area of the core should be uh, for a certain rated voltage. Okay, so we've talked about the theory a little bit. Now let's get into the transformer itself. The transformer is made up of several components. We're going to talk about the ones that are essential. Let's start from the very central part of the transformer, which is the core. It is the magnetic circuit, right? We have the electrical circuit, which is the windings, and we have the magnetic circuit. Now, what the magnetic circuit does is it provides a low reluctance path for the flux linking the primary and secondary winding. For the voltage to induce, for the right voltage to induce in the secondary winding, it's important that the flux links properly with the secondary winding. If you do not have sufficient flux linkage, then you're not going to be getting the necessary voltage. So for a transformer to operate efficiently, it's important that the core be able to link that flux. And for the core to be able to link that flux, it has to have certain properties. That's why the core is made up of high permeability steel. High permeability ensures that the flux is linking is maximum. If you had an air core transformer, it won't be nearly as efficient as a conventional core transformer. Besides, when we draw diagrams for transformers, we typically say that the winding is on the primary winding is on one side, the secondary winding is on another side. If you actually look inside a transformer, you'll see that both windings are located on the same leg. They are concentrically wound over the same leg. And the reason why that is done is to make sure that the maximum flux links with the secondary. And if the windings are wound concentrically over each other, and that ensures that maximum flux linkage. The core is in the form of not a solid piece of iron, but it's in the form of thin insulated laminations of high permeability steel. Okay. I use the term reluctance here to get an understanding of that term reluctance. Let's compare these magnetic terms with electric terms. So in electric terms, what we say is a certain amount of voltage is required to drive a certain amount of current through a resistance, right? So let's say you have a piece of conductor, you're trying to inject current through it, you apply a certain amount of voltage. Now that voltage is essentially the force. In magnetic terms, MMF is that force, which is in turn ampere turns. Okay, so magnetomotive force is the ampere turns. So it's depending on the number of turns in the coils, depending on the current that's flowing through the coil. Current in magnetic terms is flux. So the lines of flux that develop in the core, that corresponds to the current. And the ease with which that flux is able to flow in the core is going to depend on the reluctance of the core. reluctance offered by the core is analogous, is comparable to resistance offered by a conductor. So that reluctance depends on the properties of the material, it depends on the permeability, it depends on the length of the path, it depends on the cross-section of the core, just as the resistance of a conductor depends on the resistivity, depends on the length of the conductor, it depends on the cross-sectional area. So it's kind of very comparable. These terms are very comparable to each other. Okay, moving on. The way the core is designed, there are two types of core designs. There is the core form and there is a shell form. Core form is what you typically see in power transformers, where you have a core and the windings are present over the core. So that's the core form. And then you have the shell form where the windings are present in this manner. So you have the high voltage winding here sandwiched between the low voltage windings, and the core is built over the windings, so it forms a shell over the windings, which is why it's called the shell form. The shell form was actually started here in the US. I think Westinghouse came out with the design and then gave patents to other manufacturers. So shell form transformer is still in use in some applications, but typically you will see that core form is what's used more often, and that's more popular. The reason being it's easier to build a core form transformer than a shell form transformer. Shell form has some advantages in that it offers more mechanical strength and stability, but core form is easier to build, which is why you typically see that the design is a core form design. These are some construction types or arrangements provided that you can see here on the right. The one that is popular in mid-size power transformers, smaller power transformers, is a three-leg construction where you have a three-leg core. The leg refers to the vertical section of the core, and the horizontal sections are called yokes. So you have the top yoke and the bottom yoke. So in smaller transformers, you have the three-leg construction, and coils are lowered. High voltage and low voltage coils are lowered on each of these legs, so A, B, and C. In bigger transformers, you will see auxiliary limbs on the core. So you have a five-leg core where you have auxiliary limbs on the extreme ends. Now, these auxiliary limbs serve a dual purpose. They serve as a return path for zero sequence flux. Zero sequence flux, if it has without the presence of these limbs, the return path for the zero sequence flux would be through the tank. So that can result in overheating of tanks. So to prevent overheating from happening, to prevent localized overheating from happening, what is done is these auxiliary limbs are provided. Another advantage of having these auxiliary limbs is it effectively reduces the cross-sectional area of the top and bottom yoke, which in essence reduces the height of the transformer. So if you have certain height-related restrictions during transport, you can overcome that by providing auxiliary limbs and reducing the height of the transformer. There are losses which occur inside a transformer when it's in operation. There are two types of losses: load losses and no load losses. No load losses are essentially the core losses, and these losses are the same irrespective of the load which is connected on the transformer. So these losses would continue to exist even if the transformer was just energized, wasn't connected to anything else. There are two types of core losses. These are called hysteresis losses and eddy current losses. Hysteresis losses occur due to the friction between magnetic domains. Right? The core we know is a magnetic material. It gets magnetized when a voltage is applied on one winding and it draws exciting current. It magnetizes the core, and the direction of the magnetic field changes every half cycle. Well, the level of magnetization kind of follows that magnetic field. It does not, it is not in phase with it, but there is a bit of a lag, which is what this BH curve represents. So what it's basically telling us, I'm not going to get into too much detail on this BH curve, but what it's telling us is that the magnetic domains take some time to follow the magnetic field. For example, H on the x-axis, H represents the magnetic field. It's actually the magnetizing force, and B is the flux density, which basically represents the direction of magnetization of the core. So you can see here on the x-axis at the point C, my H is 0, right? It's going from positive to negative. It's 0 at this point. But at C, my B is a positive number, which means that my magnetizing force is already in the process of reversing, but there is still some time left for the core to change from positive to negative. The point at which that reversal happens is D. So from C to D, the core is magnetized in the positive direction, but the force is in the negative direction. So that's basically telling you that there is a bit of a lag, and that lag exists because of this friction that occurs between the magnetic domains. So the area that's covered by this loop, it refers to the losses that occur in the core. So what you will see is that for certain types of steel, the area is much bigger. For certain types of steel, it's much smaller. So it's preferable to have a narrow BH loop, and that's achieved by using grain-oriented steel. By using grain-oriented steel, which is processed in such a manner that that the losses are minimal, you kind of achieve a reduction in hysteresis losses, so that makes the transformer more efficient. I mentioned how the core is made up of thin laminations of steel instead of a solid piece of iron. The reason why thin laminations are used is to keep the eddy current losses to a low number. Eddy current losses occur because of the concept that I spoke about earlier, where I said if a conductor is brought in the vicinity of an alternating magnetic field, then a voltage is going to get induced, right? Well, the core is also a metallic structure. So the core is also going to feel the same effects as a conductor. So you're going to have local voltages being induced on the core sheets, and those voltages are going to result in local circulating currents. These local currents are called eddy currents, and those currents are going to cause losses, which are called eddy current losses. Among other things, the eddy current losses depends on the thickness of the material. This T here stands for the thickness of the material. And by ensuring that the thickness is kept to a low by using those insulated laminations, we ensure that the eddy current losses are kept to a low number. Okay. Uh, as these core losses, they are a constant number, but as the transformer ages, as the core ages, these losses might increase by a little bit. There are several ways in which the core can go bad. Laminations can get shorted, core can get corroded. The sheets can come loose. The sheets are held together by a clamping structure, by flinch plates. They can come loose, resulting in an air gap, which increases the reluctance, which makes the transformer core less efficient. So things of that nature can happen as the transformer ages or deteriorates. Now let's get to the electrical circuit, which is the winding. So you have the core, which was the magnetic circuit. You have the windings, which are the electrical circuits. Winding is in the form of copper or aluminum. Copper is the popular option. It's the better material to use, and in a lot of aspects, and that's why you will see that typically copper windings are used in big power transformers. In smaller transformers, where it's possible for economical reasons, possible to use aluminum. Aluminum windings are used in smaller transformers. You'll see windings in the form of foils or sheets in small pole-mounted distribution transformers. Now, when you get into bigger transformers, you will see that the conductors are basically parallel strands having a rectangular cross section, which are arranged in what's called a continuous transposed conductor arrangement. Now, the reason why the CTC arrangement is used is to make sure that the winding stray losses are kept to a minimum. So if this CTC arrangement didn't exist, then a voltage drop would be created between the strands themselves. So you would have local circulating local stray losses in the winding itself, and to avoid that, what's done is the winding is arranged in the form of the CTC. High voltage winding typically is built in the form of a disc winding. It's what this looks like. A disc winding arrangement provides mechanical strength. It's able to withstand better the mechanical forces that can arise because of faults. So that's why you typically see that the high voltage winding is a disc winding. Here are some other winding constructions. You can have a pancake winding, which is used in a shell form transformer. Disc winding we have already seen, and layered winding can be used in low voltage windings. Helical winding is where it's in the form of a screw, and that's also used to build a winding. So the way the transformer is built, if you talk about a core form transformer, you build the core first by arranging the laminations, by stacking the laminations together, and those laminations are horizontal, and then it's made vertical. So now you have the core built completely, and then these coils that were built are then lowered onto the core legs, and the next stage is to make the connections. So the connections are done in this manner. You can have a star connection, you can have a delta connection. In some special applications, you might come across a zigzag connection, but typically what you'll see is a delta connection or a star connection. In a star connection, what's done is the bottom ends of each coil is joined together to form a neutral. So typically you'll see that if you have a Y-connected winding on your transformer, you'll see 4 bushings, right? You have the 3 line bushings and a 4th neutral bushing. In the case of a delta connection, the coils are connected end to end to form a triangle or a delta. And the way in which these connections are made depends on the vector group of the transformer. So if it's a DYN1 transformer, which is a pretty popular vector group, the A phase lies between H1 and H3. If it's a DYN11 transformer, then the A phase lies between H1 and H2. Okay, so the connections are made based on the vector group of the transformer, which is provided on the nameplate. If not the vector group, the vector diagram is provided, and you can see the connections on the nameplate as well. We'll get to that later in the section. And then you have a zigzag connection where basically each leg has 2 halves of a winding, and one half of one winding is connected to another half of a winding on another leg. So you have this type of an arrangement where it's called a zigzag winding, and the basic advantage of having this is that it provides a very high impedance path to positive sequence currents, but it provides a very low impedance path to zero sequence current. So this can be used. One case where this is used is, for example, on neutral grounding transformers. You will have basically it's a single winding, right? So you'll have a zigzag winding which is connected and used as a neutral grounding transformer. Okay, so let's move on. So we have the core and the winding coils are lowered on it. The connections were done. So what we have now is the core coil assembly. The winding has insulation on it, and the next stage would be to after processing and everything, it's the core coil assembly is tanked and it's filled up with oil, and that completes the transformer. The insulation is made up of the solid insulation which is already present on the active part, but it also consists of the liquid insulation which comes in later on, right? So the solid insulation is in the form of cellulose. It is in different. It is used in various forms like pressboard blocks. You're gonna have pressboard barriers. You're gonna have spacers. You're gonna have paper. You're gonna have prep paper on joints. So all of these different types of insulation are used, but it's essentially cellulose. And cellulose is a naturally occurring polymer, which means that it's made up of chains of thousands of molecules. And as the cellulose ages, this chain ruptures at different points, resulting in a process called depolymerization. And as depolymerization occurs, the cellulose loses its properties, becomes brittle, it loses its strength. Um, for liquid insulation, what you're going to see is typically mineral oil is going to be used. You might also come across some alternative fluids like esters, but typically what you would see is mineral oil. Mineral oils are mixtures of hydrocarbons. You can have different types of compounds. You can have naphthenic compounds. You can have paraffinic compounds, and they are present in various proportions. And based on the proportions in which they're present, oil has that oil would have its unique properties. Oil not only acts as insulation, but it also acts as a coolant. It flows within the transformer, helps in the dissipation of heat that's generated inside the transformer, right? Uh, a third purpose that it serves is diagnostic in nature. So if you undergo a blood test, then the blood test results tells you about your health, right? Similarly, if you do certain tests on oil samples, that those oil test results tell you about the health of the transformer. There are several processes which occur inside a transformer as it ages, which result in the degradation of insulation. One factor which affects the rate of degradation is heat, the temperature at which the transformer is operated, which is going to depend on the load that's connected to a transformer. It's going to depend on whether the transformer has been subjected to falls from time to time. But the temperature adversely affects the insulation. Higher the temperature, lower the insulation life of the transformer. Cellulose undergoes oxidation naturally, and that results in the formation of carbon oxides and water. In the presence of carboxylic acids, it can react with water to undergo a process called hydrolysis, which results in broken polymers. Oil undergoes oxidation to form carbon dioxide and water. There are several chemical byproducts which are formed as a result of the intermediate processes that include alcohols, aldehydes, ketones, peroxides, and acids. If the acid content becomes too high, then that can result in the formation of sludge, which not only obstructs oil flow, but it can also attack cellulose. So it's harmful to the transformer. There are several gases that are generated as a result of the degradation processes in oil. Uh, Partial discharge results in the formation of hydrogen. Hydrogen requires the lowest amount of energy to form. So any partial discharge will result in the formation of hydrogen. And then if you have thermal faults, that will result in the formation of other gases. Depending on the severity, you can get different gases. At low temperature faults, you can get methane. And as you go higher on the temperature, you can get additional gases like ethane and ethylene. If you have out and out arcing inside the transformer, then that will result in the formation of acetylene. So in your DGA test results, even if you see 1 ppm or 2 ppm of acetylene, that's cause for concern. The transformer needs to be taken out of service immediately. So that means that there is arcing occurring inside the transformer, which is detrimental and can result in failure, right? So acetylene is absolutely a no-no in your DGA test results. The processes that occur inside the transformer regarding the insulation are influenced by several factors. These include external factors and internal factors. External factors include absorption of oxygen from the atmosphere, moisture ingress, solid debris can enter as part of maintenance activities, and internal sources also include moisture. Moisture is produced as a result of some of the processes that occur inside the transformer. Metal particles can come loose from mechanical wear and tear. Cellulose particles, cellulose fibers can come loose from the solid insulation. Chemical degradation products, we already talked about how those products are formed as a result of some of the processes. Now that was some information about the insulation. Okay, now let's talk about bushings. Once the transformer is tanked, bushings are connected, and those are the only those are some of the important parts of the transformer that are visible from the outside. They serve as the interface between the transformer and the rest of the system. One thing in which they are unique is that they have to be able to they are pretty small, and they have to be able to carry a high amount of current. Not only that, they have to be able to withstand the voltage that appears during normal operations, right? Besides that, they are also exposed to the external to the elements, so they are quite an important part of the transformer, and they are also a part which are likely to be the cause of a transformer failure. Bushings and tap changers are two of the top reasons for failures, for transformer failures. So it's very important to keep an eye on bushings. they can be classified into classified on the basis of various categories. If you look into insulating media, they can be classified into air to oil, air to air bushings, oil to oil, air to SF6, SF6 to oil. Typically what you see is air to oil bushings, right? But if you have a transformer which is used in some applications, like for example, if you have a transformer connected to underground cables, then you would need oil to oil bushings to interface with the underground cable. If you have a transformer which is connected to a GIS bus duct, then you would need SF6 to oil bushings to interface with directly with the GIS bus duct. According to construction, the bushings can be classified into two types. When you get into low voltage applications, distribution level, what you see is the solid type design or the solid type construction, where it's just a single dielectric which is present inside the transformer. Could be air, could be oil, but it's a single dielectric. And when you get into high voltage applications, what you come across is the capacitance graded design or condenser design, which is more of a composite dielectric, and we're going to talk more about this in the next slide. According to insulation inside the bushings, bushings can be classified into uh, air insulated, oil filled, oil impregnated paper, which is the popular form of condenser bushing design. You can also have resin bonded paper, you can have resin impregnated paper, cast insulation, gas insulated. These are also the solid type construction bushings. The bushing that you will come across that's very popular and widely prevalent is the OIP bushing. So that's what you will typically come across. Here's some information about the condenser bushing design. So in an OIP bushing, the way it's built is you have a central conductor which carries the current, right? Around that, uh, a conductive foil, which typically aluminum, is wound and impregnated in oil and wrapped in oil impregnated paper is wrapped multiple times around the central conductor. Now, because of that, what it creates is several layers of insulation. So several capacitances are created and they are in series with each other. One of the outermost layers of the foil is connected to a test tap, which is a pin which is brought out at the base of the bushing. So when you look at a condenser bushing, you'll typically see a test tap at the base. It will have a cap which essentially grounds it when the bushing is in service. But to be able to test the bushing, you need to unscrew that cap and make the connection on the test tap. On the nameplate of the bushing, you will see a C1 value and you may also see a C2 value. The C1 value that you see is you will see a capacitance and a power factor value for it. That capacitance is the capacitance of the insulation that exists between the conductor and the test tap. Right? So all of these capacitances connected in series with each other together are represented as one equivalent term, which is called C1. The test tap itself is isolated from the ground. If you take off that cap, then it's isolated. And that insulation that exists between the test tap and the ground, which is essentially the mounting flange of the bushing, that insulation can also have a capacitance, also has a capacitance which is called C2. Now let's talk about tap changers. Tap changers are typically seen in transformers, and the purpose that they serve is they allow variation of voltage by changing the number of turns of winding in circuit, right? So there needs to be a certain level of fluctuation that you can use, a certain level of flexibility available in the voltage that you get on the primary side or on the secondary side. So that flexibility is provided by adding tap changers, and tap changers are of two types based on how they can be used. And one is DTC, de-energized tap changer, and the other one is load tap changer. The difference between the two is in a de-energized tap changer, the circuit opens up when the tap is being changed, which means that it's not safe, not at all safe to operate the tap changer while the transformer is in operation. Even if nothing's connected to the load, even if it's just energized, you cannot operate the DTC while it has voltage on the while voltage is on the windings of the transformer. So that's the reason it's called de-energized tap changers. Another term which was used earlier is no-load tap changers, which technically not correct because the transformer could be on no load and still be energized. So the technically correct term to use is de-energized tap changers. Load tap changers, on the other hand, can be operated when the transformer is in service. So it allows for tap change. It uses a technique called make before break, which allows you to change the tap without there being any disturbance inside the transformer. The transfer of current from one tap to the other is pretty smooth. Uh, based on what's used inside these LTCs, they can be primarily classified into two types: resistance type and reactance type. Before we get into the LTCs, let's just take a look at a DTC arrangement that's shown here, just to give you an idea of what happens inside the transformer when you change a tap. So on a DTC, what you'll typically see is 5 taps, and you rotate. It's typically a rotary switch, so you rotate it, and that changes the tap. And what's happening inside the transformer is you have a winding which has taps provided on it, and there is a definite number of turns which exist between consecutive taps here. So between 5 and 3, you have a certain number of turns. Same number of turns exist between 3 and 1, 2 and 4, 4 and 6. Let's say we have the switch initially at this position where 1 and 2 are connected to each other, right? So on the left side here, you have 1 and 2 connected to each other. Now, if I move this switch from A to B, then what's going to happen is this is going to move here and it's going to short out 2 and 3. When I short out 2 and 3, what's happening is 2 and 3 are getting shorted out, which means that effectively I'm shorting out the section that exists between 1 and 3. So this step gets shorted out. I have that much less turns, which means that I reduce the effective voltage on my winding by a certain percentage. If I move the switch further to 3 to 4, then 3 to 4 gets shorted out, which means I'm shorting out 2 steps now. I'm shorting out the step between 2 and 4 and 1 and 3. So I should be getting even less voltage because I've reduced my turns by that much, by one more step now. So as I move this switch to the right until I move to 5 to 6, where I've shorted out the entire section that exists between 5 and 6, what I'm doing is with each tap, I'm reducing each step, and I'm reducing the voltage by that proportion. That proportion is typically 2.5% of the rated voltage. So what you will typically see is 5 taps: A, B, C, D, E. C would be your center tap, it's the nominal tap, and then you can achieve a plus 5% variation, you can achieve a minus 5% variation, and this is how the variation is achieved. You rotate the switch, that changes the connections internally, and that effectively changes the number of turns. So it's pretty simple here, because we are not concerned with changing the tap while the transformer is in operation. When you get into LTCs, though, there are some, it gets a little bit more complex comparatively. So what you have is resistance type LTCs and reactance type LTCs. In resistance type LTCs, resistors are used in transition. So these resistance type LTCs are not that popular here. They're more popular in Europe and elsewhere in the world. In the USA, we use reactance type LTCs. What happens in a resistance type LTCs is typically what you will have is a diverter chamber, which houses an arcing switch. You have a tap selector here. So this is where all the tap connections are made. This tap changer is present inside the transformer tank. This chamber has its own oil, so it's isolated from the transformer tank. And because this is where the actual arcing occurs, so we do not want this to be exposed to the main transformer oil, right? So this is a separate chamber in itself. And this is where the connections occur, and this is where the tap selection occurs. So tap selector can be represented by this upper section on the figure here, and this lower section here represents the arcing switch. Okay, so what happens is when you initiate a tap change operation, what happens is the first step, the tap selector operates. So we have what we call as a pre-selector. So the pre-selector selects the tap that we want to move to when we initiate the tap change operation. So the one on the left is my initial tap. The one on the right is the tap that I want to move to. So this switching has happened even before the transfer of current occurs. So that's why it's called the pre-selector. So this is the tap that's in operation right now, right? So you have the arcing switch connected to it right now. You have the connection done on this particular tap. Now, when the pre-selector operates, when the tap selector operates, what happens is the operation is done through a drive mechanism, and that drive mechanism basically energizes a spring energy accumulator. So the spring energy accumulator gets tensioned, and at the end of this operation of the tap selector, the arcing switch is actuated by the spring energy accumulator. It releases the energy actuating the arcing switch, and the arcing switch then operates. It goes into this intermediate position where it comes in contact with the transition resistors, which limit the circulating current, and then it switches over to this position where the new tap is already selected. So we achieve a transfer of current here by using this type of arrangement. The transition resistors limit the current. They are loaded only for a few milliseconds, uh, and then you get into the new tap. The whole operation takes about 3 to 10 seconds, but the majority of the duration is taken up by this operation of the tap selector. The arcing switch itself takes a few milliseconds, about 40 to 60 milliseconds typically, and the bridging resistors, the transition resistors come into play for even a shorter duration, which is typically 20 to 30 milliseconds. So that's the way resistance type LTC operates. And if you come across a reactance type LTC, which if you're here, what you will typically run into is reactance type LTCs. In a reactance type, as the name suggests, a reactance is used to limit the circulating currents instead of a resistance. And the difference between the two is the bridging position is actually used as a tap position. So this is the reason why reactance type LTCs, I guess, are more popular here, is because you get more finer variation. You get twice the number of taps for the same winding, uh, and that's because you use the bridging position as well. A typical design that you will come across is vacuum interrupter with tap selector, where the vacuum interrupter is used for the transfer of current. The reactance is in the form of a preventative auto transformer, which is a smaller transformer which is actually present inside the transformer. It's not magnetically coupled with the winding of the transformer. It's basically two halves of a winding with a 1-to-1 turns ratio. And the way they're connected is if you have a bridging position here, a bridging position in which the connections are made on consecutive taps, right? So you have let's say tap 4 and tap 5 connections are made on both taps. So what you will have is, in a bridging position, load current will flow through both arms here, right? And then they will flow out here from here. When the load current flows, the ampere turns on the preventative auto on each half of the preventative auto cancel each other out, with the result that the preventative auto does not impede the load current. But if you have a circulating current, the circulating current is going to be circulating current is going to be in this form. So it's going to circulate in this loop. And in that case, the ampere turns do not cancel each other out. The circulating current is presented with the magnetizing impedance of the preventative auto, which essentially blocks it. So you do not get circulating currents because of that preventative auto. Now let's see how a transfer of current occurs in a reactance type LTC, which uses a vacuum interrupter with a bypass switch. So you have these 6 stages. Initially, the connection is on tap 4 here. So what we are going to see is that in this position, you have the current flowing through both sides, right? You have a vacuum interrupter here which is closed. You have the bypass switch P3 here, which is also closed, with the result that the current is flowing through both arms, but the connection is on just one tap. So this is not a bridging position. This is a non-bridging position. Then to change the tap, when you initiate the tap change operation, what happens is the bypass switch opens first. So you have P3 open, but the current still flows through the other side because of the vacuum interrupter. The vacuum interrupter is closed, so that conducts the current. So you still have currents flowing through both arms. Now the vacuum interrupter opens, interrupting the current flowing through here. So we do not have any current flowing through the right side. What we get is just this current. So the current flows from P2 to P1, and now that this arm is open, what we can do is move P4 from 4 to 5. So P4 has moved from 4 to 5, and now we are on the bridging position. Now the next step is to close the interrupter. The interrupter closes, so you have current flowing through this arm as well, in addition to this. And then the bypass switch closes. So the bypass switch is not the last, it does not have to deal with the interruption of current and the reclosing of the circuit. It's the vacuum interrupter which works to do that. And then you have a bridging position where you have current flowing through both arms, and the tap connections are on two different taps, 4 and 5. So that's how a reactance type LTC transfers current using a vacuum interrupter along with a bypass switch. For tap variation, you have a winding which does not have any taps on it, and you have a regulating winding which has taps on it, and the number of turns in the winding is changed typically on the tapped winding. So the regulating winding can be connected to the unregulated winding in these different arrangements, where you can have a linear arrangement where it's just connected in series, and it's pretty simple if you look at it. The other way is to use a reversing switch, which is the more popular one. What you will see is a reversing switch is provided, and again, this information you can look at the nameplate and figure out exactly how the connections are made. So these connections you'll be able to see on the nameplate. So you will see a reversing switch, you will see a tapped winding, and the idea behind providing that reversing switch is it reorients the winding. It doesn't physically reorient the winding, it changes the connection so that the winding either opposes the main winding or it adds to the main winding. So depending on which way it goes, you can either get positive variation or negative variation, but you effectively get twice the variation for the same amount of steps on the winding. Okay, so that's why it's preferred. You do not have to, if you were to use a linear winding, you would need twice the amount of winding for the same amount of variation. So that's why it's more economically feasible to use this changeover switch or reversing switch to achieve that variation. On some special applications, you can come across coarse and fine variations as well, where you have coarse taps, you have fine taps, and depending on the level of variation that you want to achieve, you can change the coarse taps or the fine taps for both of them. Now let's get into the testing itself. We have talked about the insides of a transformer. So now we have understood what's going on inside a transformer, what kind of things are present inside a transformer, at least the important ones. Now let's get into interpretation of nameplate data. If you are not that familiar with transformer testing, and if you want to find out, if you want to try and understand the information that's provided, it's very important to, if you want to try and understand what's going on, if you want to be able to test the transformer without any problems, it's important for you to understand the kind of information that the nameplate provides to you. So let's go over the nameplate and see what kind of information do we get. In the upper section of the nameplate, you will typically see the manufacturer's name. You'll see the nameplate. You will see the capacity of the transformer, which is essentially the loading on the transformer, right? So you will see a base rating. You will see higher ratings. So here you see 18,000, 24,000, 30,000, and then you see the cooling types corresponding to those capacities. So for 18,000 you have ONAN, for 24,000 you have ONAF, 30,000 you have ONAF. So these cooling types, what they're saying is, as long as the cooling type matches the capacity, the temperature rise of the transformer won't exceed the limit, which is 65 Celsius. Rise means the difference between the temperature of the transformer and the ambient temperature. Okay, so up until my load is the load on the transformer is 18,000 kVA. The cooling can be ONAN, which means oil natural, air natural, which means that the process of cooling is natural. Oil natural means that the oil, hot oil rises up inside the transformer, cool oil goes down, and so oil naturally circulates within the transformer. The process is called convection. air natural means that you can have radiators on your power transformers where oil flows through the capillaries in the radiators and gets cooled by the air which is flowing the spaces between the radiators. Right? So that is called natural air cooling. If you have air forced cooling, what that means is that you have fans on the radiators. These fans come on, so they force the air between the space in the radiators, thus more effectively cooling the oil in the radiators. Now, you can see here that for 24,000 you have ONAF, for 30,000 you have another ONAF. What's the difference between the two ONAFs? The difference lies in the number of fans which are switched on. So let's say you have two groups of fans, two groups of 2 or 3 fans. So as long as the loading is under 24,000 or between 18,000 and 24,000, you're going to have one group of fans switched on. If the loading exceeds 24,000, then the second group of fans is going to be switched on to aid in the cooling of the transformer, thus keeping the temperature within the limits. This fan is operation is not done manually; it's automated, and those setting changes can be made in the oil in the control cabinet for the transformer. What you see is the rated voltage of the windings as well. So the high voltage winding in this case is 34,500, the low voltage is 13,800, and the phase voltage is 7,967. So here you see two numbers. What does that tell you? It tells you that the low voltage winding is a Y connected winding, and 13,800 is the line to line voltage. So it's the voltage that exists between the phases, between A and B, between B and C, between A and C. And 7,967 is the voltage which would appear between the line bushing and the neutral bushings. So between, let's say, X1 and XO, or X2 and XO, X3 and XO, this is the voltage which would appear between those bushings. There is an impedance value which is punched on the nameplate, and that value is punched because it's actually measured as part of factory testing, and once they measure that value, they punch it on the nameplate before they dispatch the transformer. So that's why you'll see that all the other values are pre-etched or pre-printed except the impedance value. And here it says that the impedance value was measured at these parameters, at this load, 18,000 kVA, which corresponds to a certain current, and from the high winding to the low voltage winding, and the high winding was on the nominal tap. The class of the winding, the insulation class of the winding is given here, or the rated voltage class, which is 34.5. Temperature rise is 65. BIL is basic impulse insulation level, which tells you about how it's going to withstand the lightning surges. So if you have a lightning strike close to the transformer, the surge that will arise because of it. If a surge of 200 kV peak strikes the winding, then the winding should be able to successfully withstand that surge. Similarly, for the low side winding, if the surge peak voltage is 110 kV peak, then the low voltage winding should be able to withstand that surge. So system frequency is at 60 hertz. The operating altitude is at 3,300 feet. You have the winding material, which is copper here on both windings. The core type is core form. Remember, we talked about core form and shell form. Okay, so let's move on to the middle section here. It shows you what the connections are, what the vector diagram is. Remember, we spoke about vector group and vector diagram. So this is a DYN11 transformer, and here it shows you how the connections are done for a DYN11 transformer. So you have the high voltage winding coils here, which is in the form of a delta. Right? So the high side is a delta, and the low side is a Y connected winding, which means that the bottom ends of each coil are connected to X1, to XO, which is the neutral which is brought out. Right? So let's try to figure out which phase exists between which winding. So if you have between which terminals. So if you have if you look at the connection diagrams here, this says phase A. Phase A, if you look on the high side, it starts off at H1 and ends at H2, right? So the A phase winding, if I look at the vector diagram, I'll see that it exists between H1 and H2, which is the line of the triangle which is parallel to X1, XO, which we clearly know is the A phase. Phase B exists between H2 and H3. Right? This is H3. So if I look at phase B, I can clearly make out that this is the side of the triangle which is parallel to X2, XO, which I know is the B phase. And then for my C phase coil, the C phase coil exists between H3 and the other end is actually at H2, right? So the C phase exists between H3 and H2. If I look at the triangle, the side of the triangle that's parallel to X3, XO is H1, H3. So that's how I know there are two ways in which you can do it. You can actually look at this diagram and figure out which phase lies between which, or you can simply look at the vector diagram itself and figure out which phase lies between which phases. So it's as simple as that. It's helpful to know which phase lies between which terminals if you're doing diagnostic testing, right? If you see a wrong value on a, let's say between H1 and H2, you need to know which phase is corresponds to that coil to be able to do further investigative testing. Let's look at the lower section of the nameplate. Now here is where it gives you the tap information. So here it's telling me that this tap changer has 5 tap positions, and it's telling me the connections that occur inside the transformer. Here I can see the rated voltage corresponding to each tap. Here it gives me the rated currents for each tap at different loads. So the left column is for 18,000 kVA, this is for 24,000, this is for 30,000. I can see the low voltage rated current as well. So these currents are provided for maybe for doing a test or for entering these values in a report. You might need the values. These values, if you cannot find them on the nameplate, they can also be calculated. So I could, for example, if I want to calculate these values, how do I do that? So the value that corresponds to 18,000 kVA is given here, is 301. How do I calculate it? By using a calculator? It's very simple. I just take 18,000 kVA. So since it's a kVA, I'm going to be doing this. Divided by the root of 3 times 34,500. That's going to give me 301 amps. So you will typically see the rated currents, but in case you're wondering, how do I get that value? It's very easy to derive it from the rated voltage and the rated kVA or MVA. And then below that, you can see the mechanical information, the weights of the core coil assembly, the tank and everything. And below that, you can see the liquid that's present, which says Envirotemp FR3, which means that it's a synthetic ester. Okay, so now let's come into the last section of the transformer, which is of this presentation, where we talk about the tests that are done as part of commissioning. Okay, so you have this table in the IEEE field testing guide, which is C57152, which mentions all the different tests which are recommended, or as AN stands for as needed or optional. So you can refer to this table to figure out which tests need to be done. We're going to talk about the ones that are highlighted here. This is just part of the chart. There's another portion of the chart which doesn't deal with specifically the electrical tests that are done on the main transformer, so I've omitted that section. We're going to be discussing the tests that are done that are provided on this chart. So commissioning test, we are going to be focusing on commissioning when we talk about these slides, but the same tests can be done as part of regular field testing, as part of your maintenance testing, right? When I talk about these, I'm going to be talking about the scenario of commissioning. So commissioning tests are the tests which are done when the transformer is installed on site. It's a brand new transformer. It has arrived from the manufacturer, and you want to make sure that you do a complete testing, the complete range of testing on the transformer before you energize it. It's not possible for us to do certain tests, certain important tests, which can be done in the factory, right? We only have a certain gamut of tests which we can carry out. Most of those are low voltage tests, but they give us a good deal of information, and that is the only information that you have prior to actually energizing your transformer. So it's a big deal, and you have to make sure that you carry out these tests in the right manner and you are able to interpret the test results so that you can make sure that you are really confident that you want to energize this transformer. So we're going to start off with the very basic test, which is the turns ratio test. In this turns ratio test, we measure the turns ratio. We already spoke about how the turns ratio is proportional to the voltage ratio, right? So if I have a 34.5 by 13.8 kV transformer, to make sure that that if I apply 34.5 on one side, I get 13.8 kV on the other side, I can verify that relationship by applying a lower voltage on one winding and getting the and measuring the voltage that's induced on another winding. That low voltage typically is between 80 volts to 250 volts. That's the voltage that's used on the high side to get the required to measure the turns ratio. That's sufficient enough. We are not only measuring the turns ratio here for a three-phase transformer, we are also verifying the winding connections. Right? I told you about how the delta connections are made, how the Y connections are made, and it's based on the vector group of the transformer, which is provided on the nameplate. If not the vector group, you will at least see the vector diagram. And if you're using a digital turns ratio test set, you are going to enter that vector diagram, or you're going to select that vector diagram or enter the vector group and then proceed with the test. And if you get the right results, if your turns ratios are all good, they match up with the nameplate values, then you are not only you not only know that the turns ratio is good, but you also know that the winding connections are done in the right way. Right? So it also checks the winding connections, and it can also detect shorted turns. So let's say you have a dead short in your winding, then if you apply a voltage, even if it's 80 volts or 250 volts, that's if it's a dead short, it's going to cause circulating currents, and your test set will probably trip because of that. So it's a useful way of checking dead shorts in your windings. What the primary parameter that we measure here is the turns ratio error, and that error is calculated by comparing the measured ratios with the calculated ratios. The calculated ratios are calculated from the nameplate values. So if you're using a modern turns ratio test set, you would be entering the rated voltages that you see on the nameplate. You'd be entering the number of taps and all of that information, and based off of that, the turns ratio, the software of your test set calculates the ratios and shows that to you on your software screen. And then you would be, when you run the test, the measured values appear alongside it, along with the turns ratio errors. The turns ratio error for the test to be a pass, it needs to be within 0.5%. So that's the pass-fail limit for this particular test. So it's a very basic test, but when you do a commissioning test, this is it's one of the first tests that you have to perform to basically verify that it's going to perform its primary function, which is of transferring the voltage from a certain level to another level, and among other things. So this is more of a basic check which you have to do initially. Winding resistance test has more of a diagnostic value than being a basic check. So it helps you detect winding related problems. Right? In your windings, you can have burnt out, broken strands, shorted turns. You can have poor connections, which is a possibility if you're doing a commissioning test, right? When a transformer is transported, your bushings may not be unless they're really small bushings, they're typically taken out, and the connections are made when the transformer is installed on site. So if the connection is not made properly, then that can be a loose connection, which will get caught in the winding resistance test, because that will show up as a high resistance value. You would expect the windings to be in good shape if it's a brand new transformer, but connection problems can occur. Tap changer problems like bad contacts, or if the mechanism develops a problem, if there's deposition on contacts, that can result in different resistance values, abnormal resistance values, which can easily get caught during the test. The way to do this test is you inject DC current through the winding. So the reason why you inject a DC current is because the winding, as we know, has inductive properties, right? It's a coil that is there. So you have the copper, which has a resistance, but since it's in the form of a coil on a core, it is going to have an inductive it's going to display inductive properties, which means that if you apply an AC current, an AC voltage, or if you try to inject AC current through the winding, then what the source is going to see is not just the resistance, but it's also going to see this inductance. To be able to measure this resistance, we need to do away with this term LDI by dt. So what do? We inject a DC current. That DC current magnetizes the core in just one direction, right? Because the current is flowing through the conductor in just one direction, the flux flows in just one direction. So what we do is our goal is to achieve core saturation. So we just keep filling the glass up to the brim until the water starts overflowing. To be able to do that, we need sufficient juice, and that juice is in the form of the test current that we apply and also the voltage that we use to inject that test voltage. It's the open circuit voltage of the test set that we are using. So both of these parameters are equally essential in achieving core saturation. And once the core saturation is achieved, the way the test progresses is when you hit the button, it injects the current. But let's say you're doing the test at 10 amps, the current doesn't jump from 0 to 10 amps. It initially climbs up slowly. It takes a few seconds to climb up from 0 to 10 amps. That's because there is an opposition offered by the coil, and that opposition depends on the rate of change of current, right? As you can see here, this LDI over dt is the one that opposes that. But once the core saturation is achieved, this di by dt or di over dt term is cancelled. The core loses its properties. It basically becomes like air once it's sufficiently magnetized. So the coil loses its inductive properties, and what we are left with is just the resistance. The test set also has a voltmeter along with the current source. So the voltmeter measures that voltage drop, and V over I, we get the resistance of the winding. The current that we use for this test is really important. As I mentioned earlier, it has to be high enough to ensure that the core saturates properly. If it doesn't saturate, then you'll get fluctuation in your readings. You'll get a certain percentage of error in your measurements. If it's very high though, then that can result in the heating up of the winding that you're testing, and that in turn will result in a higher resistance value. So you want to keep it in a certain range. That range is typically between 1 to 10% of the rated current. How to analyze the results? The readings can be analyzed by comparing between phases. So A, B, and C, you get 3 readings. Now these readings would be within 2% of each other. Typically on the same tap position, you would get readings which are within 2% of each other. This 2% value is for power transformers. Okay, so if you're testing on a distribution transformer, those readings may not be within 2% of each other. Insulation resistance test is more of a basic check for insulation. Okay, so your winding resistance test helps you check the winding of the transformer. Turns ratio test verifies the turns ratio, verifies the connections. Insulation resistance test is directed at the insulation. So as you do different tests, you're basically checking different aspects of the transformer. Insulation resistance detects insulation deterioration or failure. What we do is we basically measure the resistance of the insulation. So we use a DC voltage source. The test is typically done at 5 kV, and there are 3 measurements which are done on a 2-winding transformer. We perform high voltage to low voltage grounded, low voltage to high voltage grounded, and high voltage to low voltage. So these tests test out the winding to winding insulation and the winding to ground insulation. The tests can be done in the form of 1-minute tests, where at the end of the 1-minute duration, you just record the insulation resistance value, which is typically in mega ohms or giga ohms. Another test that can be done is a polarization index test, which is a 10-minute measurement instead of a 1-minute measurement. So you do those same measurements, but you run the measurement, you apply the voltage for 10 minutes, and at the end of the 10-minute duration, you get a polarization index value, which is the ratio of the 10-minute value to the 1-minute value. And here are some guidelines provided for this test. I'm not going to go over these values. You're going to get a copy of the presentation. You can you can refer to these values from that. We are already over the 1 hour mark, so just going to speed things up a little bit. You have the core ground insulation resistance test as well. The core is grounded at an external, the core is grounded at a single point, and that point is brought out typically on power transformers. You will see an external core grounding terminal. That core terminal is grounded externally. What you can do is, as part of your commissioning test, you can take off that grounding link and apply a voltage using your insulation resistance test set between the core terminal and the ground terminal on any that you can find on the tank. So when you apply that voltage, you should be measuring a considerable insulation resistance. Again, you can go over these limits that are provided on this table here. But if you do not see a high enough value, if you see a 0 value, or if you see a very low value, what that means is that the core is grounded at some other point inside the transformer. Now that can be harmful to the transformer, because if the core is grounded at multiple points, that creates a grounding loop inside the transformer, and that basically means there's going to be circulating eddy current inside. There's going to be circulating currents inside the core, which is going to result in overheating, possibly resulting in arcing, and that can result in failure of the transformer. So it's important for you to make sure that the core ground, that there is insulation resistance measured when you isolate the core ground terminal. This is another test apart from the insulation resistance test, which is used for checking the insulation. This is a more advanced version. It gives you more important information than the insulation resistance test. Insulation resistance test is more of a basic check as compared to this. This test not only checks insulation deterioration, but it also detects changes in winding geometry. Right? So when the transformer is transported, let's say something happened during transport and the windings inside the transformer moved, or there was significant movement inside the transformer for whatever reason. Maybe something could have happened during factory testing, or in the process of transporting the transformer from the manufacturer to the site. That can also be checked by looking at the capacitance. So we look at two parameters here. We look at power factor, we look at capacitance. Capacitance tells us about what's going on physically inside the transformer, and power factor tells us about the quality of the insulation. So you should have your factory test reports, hopefully, and you run this test. An AC voltage, typically 10 kV for power transformers, for big power transformers, is applied across the insulation. There are 3 insulations for a 2-winding power transformer. For a 2-winding transformer, you have CHL, which is the interwinding insulation. You have CLG and CHG, which is the winding to ground insulation. And you apply the voltage, you do some measurements, and you measure the capacitance and power factor for each of these terms. The power factor should be less than 0.5% for new transformers, should be less than 1% for service stage transformers. These limits are for mineral oil filled transformers. For ester filled transformers, you can get higher values. There are more guidelines provided for limits provided for results interpretation in the IEEE field testing guide and some other reference documents which you can look up, or you can look at a power factor testing webinar that I did last year for more information on this test specifically. Excitation current is a test which is done along with the power factor test, and it detects winding and core defects. In this test, we apply the voltage across the winding, not across the insulation. So each phase of the high voltage winding is energized with all the other windings open circuited, and the exciting current is measured, which, if you recall, we talked about the exciting current in the very beginning. This test is a reference test, which means we do not have a set limit, but we compare the results with the previous tests. And if you do not have anything to compare with, what you will see is, what you will do is compare between the phases. What you would typically expect is a high-low high pattern to be obtained. A and C phase current should be close to each other, and the B phase current should be low as compared, should be almost half compared to what you get on the A and C phases. The currents that are drawn depend on the reluctance of the core path, right? And since the reluctance is low for the middle leg, you measure a lower current in the middle phase. Now let's get into some advanced tests. The tests that I covered earlier are all the basic tests that you would need to do as part of commissioning. Sweep frequency response analysis is an advanced test, but it's also a very important test when it comes to, especially when it comes to commissioning, because one thing that we want to make sure of is that nothing happened during the transport. The transport process is a very cumbersome process. It involves a lot of effort, time, and money. But if anything goes wrong, then that can eventually result in transformer failure if the transformer is energized without properly testing it. So this is one test which can be done. In fact, this should be the first electrical test that is done on the transformer once it arrives on site. This is typically the last electrical test which is done on the transformer before the manufacturer dispatches it from the facility. So the only thing that happens between the 2 points is transport of the transformer. If something goes wrong inside the transformer during transport, then that will show up as a deviation in the test results. In this test, what we do is we apply a variable frequency low voltage signal uh, on one point on the transformer and measure the response signal on the other end, and we record the response. The response is a transfer function, and we don't really care about the mathematics behind it. What we want to do is compare the test data over time, or if you do not have any previous test results, you can compare the results between sister transformers. Sister transformers are transformers that are part of the same work order. Or you can do a phase-based comparison, which is the least preferable form. But if you do not have anything else to go with, then you can compare the readings between the phases A, B, and C. A and C phases should be closer to each other as compared to the B phase, because the B phase lies in the middle. This is the last slide of my presentation. Sorry for going over time, but I want to make sure that I cover all the aspects, especially the testing bit. So in this test, what we do is this is a more advanced form of power factor testing. In a power factor test, we get a single value which we compare against limits, or we compare it with previous test results to see how the power factor value has increased. But in this case, we perform a power factor measurement over multiple frequencies, and we get a curve like this by joining all those different power factor values that are measured. So on the x-axis, you have the frequency. On the y-axis, you have the power factor. And the shape of this curve tells us about what the condition is inside the transformer. It tells us what the moisture content is in the solid insulation. Majority of the moisture is held in the solid insulation. So this is one way of determining what that moisture content is. We can also determine the conductivity of the oil, which tells us about the quality of the oil. Right? And also by looking at abnormal responses, by sensing abnormal responses, we can detect insulation failure. The information is obtained by using modeling techniques, which involves database measurements of cellular samples with different moisture contents, which involves mathematical calculations, something called the XY modeling. And again, if you need more details on this particular test, you can look at DFR webinars that were done specifically on DFR in the past. We have recordings of previous webinars available on our website. If you're interested in knowing more about each of these tests individually, you can go into those, you can look at those recordings, and you'll get far more information on this. So with that, I conclude the presentation. Let's have questions. This is my information, my email address, and also the numbers for the sales departments. Thanks, Mike.
All right. Yeah, thanks a lot, Sanket. So as he stated, we've come to the end of our webinar portion of our presentation, or the presentation portion of the webinar. We'll now take some time to answer as many of your questions as possible. If you have any questions, please submit them now into the Q&A box on the GoToWebinar control panel. For those of you that are leaving, when you close the webinar window, a survey should pop up on your screen. We would greatly appreciate it if you could take a couple of minutes to provide your feedback so we can continue to improve upon our future webinars. On the survey, there's also a field where you can request a quote or a demo of any Megger products. A copy of the presentation, certificate of attendance, and a link to the video recording of this webinar will be emailed to everyone in about 2 business days. You can also view video recordings of previous webinars, as well as register for upcoming webinars on our website at us.megger.com/webinars, and register for our next webinar on January 20th, hosted by Power Diagnostics, titled Offline PD and tan delta measurements on medium and high voltage cables using ICM system and ICM flex, We're also going to have another testing tactics webinar on February 19th titled Understanding Different Transmission Line Testing Theory and Applications. All right, let's get into your questions. The first one I'm going to be directing towards Daniel Carreño. Daniel, what are the KVA ranges for a 3-leg 3-phase versus a 5-leg 3-phase?
Thank you, Mike, and thank you, Sanket. This was a great presentation. So now on for the question, the KVA range or the capacity of the transformer is not the sole factor to consider, to determine if a 3-leg or 5-leg design for the core is better. Many factors will come into play to make that decision. One of the most important is the application of the transformer, the use of the transformer in the field, for example, and without taking too much of the next question that I see here in the list. For example, if triplet harmonics is a concern for the system where the transformer is going to be installed, then a 5-core, for example, will be better than a 3-leg core. Also, the size going to a 5-core leg will reduce the height of the transformer. And of course, for example, if a large transformer is being constructed and shipping or transport is a concern, right, for regulations during transport. Again, going to a 5-leg core design will reduce the height of the unit.
Thanks, Daniel. Next up is going to be for Charles Nybeck. Charles, in regards to slide 14, could you please explain the advantage of the 5-leg core and when they should be used?
Sure. So Daniel gave me a good segue into that. Thank you, Daniel. So as Daniel said, there's two main advantages, and one is size and the other is for harmonics. So the yoke is the overhead leg that, as Sanket was saying, and a 5-leg core can reduce the section of the yoke by about 60%, as compared to a typical three column core or 3-leg core, and still maintaining the full transformer power and unchanging the dimensions of those columns or those the vertical legs. So as Daniel said, if it's for transit or maybe it's in a indoor transformer and you don't have the height requirements, then the 5-core leg will help there. This also helps when you have triple harmonics in 3-phase transformers, as this can cause some of your some of the flux to be forced outside the magnetic core and can cause heating of the tank walls and end frames of the core and such. So this 5-legged core is practical in those practices where you want to have the outside legs to have that flux return there. So again, helpful for whenever you have harmonics, beneficial so you don't have heating of the transformer. And again, if you have any size requirements as far as height, a 5-legged core can significantly reduce the overall height of the transformer.
Thank you, Charles. Back over to Daniel. Daniel, how do we test vector groups of transformers? What all conditions need to be satisfied to prove the vector group?
Thank you, Mike. Good question. And I mean, just a basic test that is performed for practically any transformer, right? The perspective of size and application is a ratio test. And the vector group typically is indicated in the nameplate, right? But if you're dealing with either a very old unit where maybe the nameplate is not legible anymore, or again, in very, very old nameplates, sometimes the vector group is not indicated. So modern TTR units, like our TTR U3, can help identify that. You just have to indicate in the unit if you have a delta or a Y on either side of the transformer or the pair of windings you're testing, and the unit will help you find the phase displacement between the two. So again, that is really easily done with modern TTR instruments.
All right, thanks a lot. Next, back over to Charles. Charles, what is the difference between test tap and potential tap in bushings?
Sure. So good question. So actually, these terms are interchangeable. So the potential and test tap are actually the same tap on the bushing there. They just have interchangeable names where sometimes it's used to be called a potential or tap or the test tap. And this tap is used to perform your C1 and C2 tests, where the C1 is your main insulation of the bushing, and then the C2 is that leftover. As you saw, Senkat had an image on the bushings where basically you have the insulation inside that creates the capacitors. So you had those series capacitors that you saw that are formed by the oil-filled paper and foil layers, and that's what causes that. That's the insulation you're testing in there using either the test or potential tap. So kind of an interchangeable term there.
I'd like to add that they are kind of similar, but you can have there is a little bit of a difference between the two. The voltage tap can have a higher rating. So typically, when you, for example, when you do a C2 test on a test tap, you do not want to exceed 2 kV because that might be the rated voltage of the test tap. A voltage tap can have a higher rating. It can go up to 20 kV. You can have one or the other, and they can be used interchangeably, but sometimes you can have a bushing which has both a voltage tap and a test tap. But the primary difference between the two is the rated voltage that can be applied on those taps.
All right, thanks a lot. Back over to Sanket. In regards to slide 18, could you please explain zigzag winding again, as well as why and when those windings are used?
Okay, let me just go back to my previous slide. Just kind of briefly, oops. Give me 1 second. Let's go to another question. I need to pull up my presentation. Just give me 1 second. Yeah.
No worries. We'll pop back over to that. In the meantime, Daniel, what is a good way to determine the winding material if it isn't on the nameplate?
Thank you, Mike. Good question. I was trying to think. I don't know of any measurement that you can do to determine that, but it might be useful if I talk about the differences, the advantages or disadvantages between the two. Of course, aluminum and copper are the main two materials that we use for transformer windings, and typically what we see is that for smaller transformers, it will be more common to find aluminum windings. And as you go up in the size, you will find copper windings. I mean, there is a debate. You can have a long conversation about this. Of course, both are good conductors. Copper being better, it can almost carry almost twice the current of that of aluminum. So that would make the the windings smaller in size. Cost is another big factor to choose between the two. But again, in general, as I mentioned, the larger the transformer is more, or will be easier to find a copper winding, even though copper is more expensive. But again, because of what I said, that being or its ability to carry more current will make the winding small, so it will counteract that part about the cost.
All right, thanks, Daniel. Charles.
I can go back. I can bring up my presentation.
We'll go back over to Sanket's question. And once again, in regards to slide 18, could you please explain zigzag winding again, as well as why and when those windings are used?
Okay, so I have that slide up now. I should be able to see it. So in this slide, basically what's done in a zigzag is you have two halves of the winding. So you have this half and this half could be on the same coil. And again, I'm just, yeah, that should be it. So this coil would be on the same leg, this coil would be on the same leg. So you're gonna have two separate halves on the same leg, but they're gonna be connected to each other, not to each other, but one half, as you can see here, is connected to a half on another leg. So by doing that, what you do is you create what's called an interconnection. Now, in the case of a zero sequence current, what happens is in zero sequence currents, you're going to have all three phases have currents which do not have any phase difference between them. All three are going to be in phase with each other, right? So let's say you have zero sequence currents which are coming in from all three sides. Now this current flows here and into the second half on the other leg, and that's basically in opposition to the current that's coming in. And same thing's going to happen on the other two phases as well. You're going to have current flow in from here, go into this particular A phase. Let's say this is A, B, and C. So essentially what you're getting is you're getting opposite currents flowing on each of these halves as long as it's a zero sequence current, right? Because in a zero sequence current, there's no phase difference between A, B, and C. All three are in phase with each other. So all three come in at the same time, and all three other halves have opposite currents at the same time as well. So they're going to oppose each other, which means amp turns is going to cancel each other out, which means that the impedance offered is going to be next to nothing. So it basically serves like a short circuit path for zero sequence currents. But for positive sequence currents, that's not the case. The A, B, and C currents are 120 degrees displaced from each other. So it's going to be different. It's not going to be, the amp turns are not going to cancel each other out. So it provides basically an open impedance or a very high impedance path for positive sequence currents. So that's the way the zigzag operates. And that's why it's used for special applications, not like a regular power transformer. It's used only in special applications where it is required that it act as uh, a path for zero sequence current. So it would be connected on a neutral of a system, for example. A system which doesn't have a neutral, it can be grounded through a neutral grounding transformer, so that the reason why you provide grounded neutrals is for you to be able to measure zero sequence currents, to maybe to initiate protection or for any other purpose. So that can be done by using a zigzag winding.
All right, thanks, Ankit. So Charles, does that turn ratio error of 0.5% come from any standard, or is it just a practical number?
Thanks, Michael. Good question. So yes, that actually does come from a standard. It comes from the IEEE C57-152, and is actually found on Table 18. That's labeled the nominal and serviceability service age limit for power transformer insulation power factor. So that's where that 0.5 came from. And that table actually breaks down between the liquid, the insulating liquids between mineral oil and natural esters, and as well as breaks down the power factor limit based on service age limit and kV rating. So I would refer to, again, the C57-152 table 18 to find those limits for power factor, or I'm sorry, for turns ratio as well.
Yeah, so IEEE
Sorry.
field testing guide, as Charles said, is the field testing guide, right? So you can obviously use that. There are also standards. I don't recall which one it is. It's probably C57.12.90, and it's basically the test code for power transformers, oil field power transformers, which you can refer to for limits as such, and that should also have the 0.5% limit. But it's basically the standard, and it's not just C57-152. You'll find it on different documents, IEC or other standards. They have the same limit of 0.5%.
All right, awesome. So Daniel, what percentage error is allowed for TTR on regulators? 16 rise and 16 lower tend to be outside of 0.5%. Are there recommendations for testing if factory results show within? Tends to be common issue with multiple regulators.
All right, thank you, Mike. And this question ties in nicely with the previous one, discussing that, or the source of that 0.5% error limit that we have for transformer. And of course, this applies for regulators too. Two things, the standard, or one of the standard documents that Sanket and Charles were discussing, like C57.152 being the field testing guide for transformers, does have a note when on the section about TTR, indicating that this could be a situation with this exact type of transformer regulators. So at least here in this side of the world, right? If we have a transformer with an on-load tap changer, will be typically on the low voltage side. And if depending on the requirements for that voltage regulation, if the voltages required or the steps required will be yield on an uneven on the visible number of turns, and that's why the results could be outside the 0.5%, especially in the extreme sides of the winding, as the person who has a question indicated, 16 raise, 16 low, that could be the case. But interestingly enough, I mean, also it's indicated in the question, right? What if our results from the factory actually show that when they did the testing, these positions were inside the limit? Well, if we actually have a couple webinars on TTR that cover this, and I remember one specific where we actually show this exact example. If we test a transformer with a low tap changer, and on the extreme sides of the winding, we show errors above the 0.5% limit. In certain cases, transformers will show a voltage dependency for a TTR. Of course, our TTR instruments, it depends on the instrument itself, but we don't use an extremely high voltage or rated voltage for TTR test. So if the transformer has this or shows this voltage dependency, that we could see these results outside the 0.5%. So just to not take more time, there are a couple alternatives or methods that we can use to overcome this situation. One is using a step-up method, right? Applying voltage on the lower voltage side of the transformer and stepping up for our measurement. Of course, this has some safety implications. You have to use an instrument that is designed to perform the test that way using step-up. And second is using a three-phase excitation. That will also help you to overcome those situations with voltage dependency for certain transformer configurations. So I would recommend to look at those two. And again, we covered this with more detail in our TTR webinar, which is available in the website.
Thanks, Daniel. I'm going to go over to Sanket for this question. What is the difference between commissioning test and maintenance test?
So commissioning tests, as I said earlier, is the set of tests that you do first when you install the transformer on site. So the transformer has been dispatched by the manufacturer, it arrives, and before you energize the transformer, you have to perform a bunch of tests on it. And those are commissioning tests. As I said, they are very important because you haven't tested the transformer before. It hasn't been in service. It has just arrived from the manufacturer's end. So you want to be very meticulous in the way you run the tests, in the way you interpret the test results, make sure that everything is good, because those are the tests that you're going to run before you actually energize the transformer. Maintenance tests are tests which are carried out as part of your regular maintenance. So every maybe 3 years or 5 years, you take the transformer out of service and you perform some electrical tests to make sure that everything is still good. So those are your maintenance tests. Again, you can do the same test that you performed as part of your commissioning, but there's going to be some differences. So for example, one example that I can think of is the TTR test, where if you're doing a commissioning test on a transformer which has a DTC, since the transformer is a brand new transformer, you want to run the TTR test on all 5 taps, A, B, C, D, E, to make sure that it's good on all taps. But then your transformer would be in service on only one tap. It wouldn't be changed in 5 years, 10 years. Now, a few years down the line, when you're doing a maintenance test, you would not be testing on all taps because you do not want to fidget around with the DETC, because that might break and then you create a bigger problem for yourself. So there's a slight bit of difference between the approach that you take for commissioning tests and maintenance tests, but that's the difference between the two.
All right, thanks, Anket. It looks like we've gone over time for today, so that's all the time we have for our Q&A session. We apologize if we didn't get to your question live, but we will be following up with you offline in the following weeks. As a reminder, a copy of the presentation, certificate of attendance, and a link to the video recording of the webinar will be emailed to everyone in about 2 business days. I'd like to thank you all for attending. If you could, please remember to answer our survey. That survey will include a field for you to request a quote or a demo if you're interested. But once more, I'd like to thank you all for attending, and I hope you all have a great weekend.
All right, thanks everyone.
Thank you. Bye.